So the next thing we're going to do with rational functions is we're going to learn to graph them. And they're actually quite interesting because they have things like asymptotes, points of discontinuity. They have holes occasionally. That's a point of discontinuity. They have certain behaviors. They use transformations. They have x-intercepts, y-intercepts, and end behavior. So there's a lot going on here, but it's not anything we haven't done before, but we're just putting it together in a little bit different way. So stay tuned. So the reciprocal function looks like this. F of x equals 1 over x. So if you were putting in some values for x and y, like our standard -2, -1, 0, 1, 2, right? Then I would have, if I put a -2 in for x, I'd have -1/2. I put in a -1, that'd be -1. Put in a 0, 1 divided by 0 is undefined. It does not exist there. 1 over 1 is 1, and 1 over 2 is 1/2. So if you put it in a graph and you did just a few key points, you would say that at -2, it would be at 1/2, -1, 1. And what you would see is that it would be a graph that looked a lot like this in the third quadrant. If I graph the other ones, right, I had 2 and 1/2 and 1, 1, then it looks like this in the first quadrant. We have two asymptotes. We have 1, which is right here, and that's the line x equals 0. That's a vertical asymptote. And then we have another asymptote along the y-axis for this graph, and that is, along the x-axis, which is the graph y equals 0. So we've graphed it, we've shown some key points on a table, and thus shown that the fact that it has both a vertical and a horizontal asymptote. It has two of them. The domain of this function goes from -infinity to 0, the vertical asymptote, and picks up again at 0 and goes to infinity. And the range looks just exactly like that. It goes from -infinity to an asymptote, starts again on the other side of the asymptote, and goes to infinity. It has no y-intercepts, and it has no x-intercepts because that is where the asymptotes are located, and it's undefined there. Transformations. You can use transformations for this. This is the parent function right here. This is the parent function. So, for instance, if I had 1 over x minus 1, like that, that would be to the right 1. If I had 1 over x plus 1, that would be up 1. And so all those same transformations work. So this is what the basic function looks like, and we're going to be graphing all different kinds of these and all different kinds of variations of this. Stay tuned. So on the previous screen, we talked about the reciprocal function, 1 over x, and that's what that looks like. The rational function looks like this, where it consists of a numerator and a denominator, where the numerator is a polynomial and the denominator is a polynomial. And we've looked at this. We've been working with adding and subtracting and all of that. We know that this is a fraction. And so, but the numerator is a polynomial, which it is here, right? The 1 over x, the parent function, that's the line y equals x. And the denominator is also a polynomial. And that's just a line as well on here. The domain will be all real numbers except where the denominator equals 0 because you cannot divide by 0. And then the parent function is 1 over x where x cannot equal, and I didn't finish it, but x cannot equal 0. Right? So here's an example. Here's an example of a rational function. Right? You can see here it has an asymptote, a horizontal asymptote at y equals 0. And then it has a vertical asymptote moved over. No, I guess not. I guess it's right there on the x-axis, y-axis. It's really hard to see, but this would be just your basic reciprocal function. So the first thing that we're going to do is we're going to find the points of discontinuity. We noticed that on the previous graph that where there are asymptotes, that is kind of like the mark the boundary of where the discontinuity is going to happen. You would have to pick up your pencil, in other words, to continue with your function from left to right. So we remembered that before that you could not divide by 0. So what we're going to do is we're going to look at the denominators of these two functions, and we're going to determine where these functions would equal 0. Right? So the easiest way to do that is just set your denominator equal to 0 and solve. So in this case, the domain of this function would be all reals except where x is equal to 2, because that is the only value for the entire function where you would divide by 0. All right, so on this one, on the second one over here, I would actually divide. I'm going to be dividing by this, so I'm going to set x squared minus 5x plus 4 equal to 0. Well, remember from a quadratic, the way to do this is to go ahead and factor. So I do x times x, the factors of 4 that add up to 5 are 4 and 1, and these are both negative. Then I would set each factor equal to 0. So x cannot equal 4, and x cannot equal 1. So the domain of this function, or the points of discontinuity, are 4 and 1. And so that would be where either an asymptote or a hole would be located, are at the points of discontinuity. Okay, so this screen didn't transfer very well from the Smartboard software, so just ignore the question mark over here for now. But this is the same problem that was on the previous screen, y equals x minus 4 over x squared minus 5x plus 4. And so what we did to find the points of discontinuity was that we factored the denominator. So we did x minus 4, and if you'll recall, when we factored the denominator, the factors of 4 that add to 5 are 4 and 1, both negative. All right, so what you can see here is that since there's minus between the factors, these two would actually cancel. All right, when you find a situation like this is a hole in the graph. This would be that whenever we graph this, there would actually be a hole there instead of an asymptote. Okay? The one in the denominator that is left would be a vertical asymptote. So, for instance, we would have, on this particular graph, we would have a vertical asymptote at x equals 1. And I'm just going to tell you right now, the horizontal asymptote would be at y equals 0 and x equals 1. And then this would go along here and along here. And where x is equal to 4, 1, 2, 3, 4, there would be a hole there. And so I made that exaggeratingly big, but that's what that is. So this graph has got two points of discontinuity, two places where it's discontinuous. And one is at its vertical asymptote, which is here, and the other is a hole. So the reason you know is that when you factor it, and you can, not everything has a vertical asymptote, not everything has a hole, and sometimes it has both, like this one, like this example. But that is how you determine them. So let's do another one. Okay, so instead of doing another problem, I think what would be better is to look at some of the diagrams, some other graphs that you can kind of see and look at its pieces. All right, so for instance, this graph right here has two vertical asymptotes. You can see that, two vertical asymptotes, one horizontal asymptote. And then this particular case, this horizontal asymptote, it comes up, you can kind of see the behavior towards them. At this horizontal, you can see as it goes this way, it gets real close to it but never crosses. And at this side, it gets close to it and never crosses. This graph goes up and then comes back down. So it doesn't cross at a horizontal asymptote. At the vertical asymptote, you can see that as it approaches from the left, it keeps going higher and higher, right? But as it approaches it from the right, it goes in the opposite direction. So you can kind of see that it goes opposite directions here, not the same. On the same side here, this one goes down, this one goes up. It does opposite doesn't go in the same direction. And then you can see the end behavior out this way towards the horizontal, that it gets close to it, but it doesn't go. Okay, it has one x-intercept, one y-intercept, and it can only have one if it's at the origin, which this one is, right? An origin, at the origin it would be both, an x-intercept and a y-intercept. But it doesn't cross either axis in any other place. Okay, here you can see it has a vertical asymptote here, and then a horizontal asymptote here. So this is the reciprocal function that's moved left and up. Another thing to notice here is that usually the reciprocal function is like first and third, but this one is second and fourth, which means it's reflected over the x-axis, so it has a negative out in front of it. It's not quite on a number, so it's, it's not like at 1, so it's hard to write the factor for that. But this just gives you another example of a possible one. Another one that isn't on here that I probably should have included. This is just the brackets, but let's say we had a vertical here. Let's see if I can do vertical, and a horizontal here. Okay, but the graph looked like this. Okay, so the behavior at the vertical asymptote meant that it was both going in the same direction. Sometimes they call this blowing up, but another way to think of it is that it's going the same direction. Here at the vertical asymptote, they were going opposite directions, right? But here they're going the same. And so what we're going to see later on is that this would be something with a perfect square in the denominator. So this doesn't always happen. Most of the time it's opposite at a vertical asymptote. So there's a lot to remember. We're going to practice and practice and practice this. This is just the first video in the graphing series. And by the end of it, you're going to be graphing like pros. So be sure that you've written this down. I hope you've listened to everything and kind of gotten an idea of what this might be in your head so that you've got the overall concepts when we get into the details. See you in class.